Welcome to the Virtual Foundry podcast.
Hi, everybody. Welcome to the Virtual Foundry podcast. This is volume 3, episode 13. Today is Wednesday, October 12th, 2022. The time is 9:11 a.m. and the temperature is a cool and rainy 61 degrees Fahrenheit. That's 16 degrees for you Celsius users. We are heading full on into fall. The leaves are starting to change color. It's really a very lovely time of year here in southern Wisconsin. Today, we're going to be talking with some folks from Halmstad University in Sweden about a project that they recently completed that focuses on the use of bronze filament. So we'll hear all about their work and their results in a minute. But first, I will introduce you to Amogh, who is a PhD student in materials systems in the materials systems department. He's researching functional surfaces of additive manufacturing applications. Say hello, Amogh.
Hello.
And we also have Senad, who is an associate professor working with mechanical design and additive manufacturing. Say hello, Senad.
Hello.
And finally, we have Professor BG, who is a professor of mechanical engineering. He started the Fab Lab at Halmstad University, and he's working on developing additive manufacturing for companies. Give us a hello, Professor BG.
Hello. Good to see you.
Now, if you're following along with the Virtual Foundry at all, you know that one of my very favorite parts of this work is working with people from all over the world and also finding out about their weather. So fellas, please tell me about the weather in Sweden today.
It's a bit grayish. It's 13 degrees Celsius. I don't know what
13.
that is in Fahrenheit. 13, 13.
Well, we're at 16 and it's 61 degrees Fahrenheit, so we're pretty close.
Yeah. Autumn is approaching here, so, you know.
In full speed.
Yeah, but leaves are still on the trees.
Oh, great.
They're getting very colorful.
Yes, so very similar to here. Excellent. Okay, so you have been working with Filamet, but we're going to hear all about that. But first, I would love to know how you all got into 3D printing. What drew you to additive manufacturing?
I think we had an idea here at the university 6 years ago in order to teach our students the modern manufacturing techniques. And at the same time, we got in contact with MIT and their concept about the Fab Lab. And we saw that if we can bring it here, then we can actually, you know, not only additive manufacturing, but also different digital manufacturing and product development and so on. So we have created here like an oasis in digital manufacturing,
Right.
Where companies, students, and we all meet here and have a great fun.
Super. Additive manufacturing is very fun. There are so many things you can do with it.
Yeah. Originally, we started with polymers and composites. So this is,
How about you, Senad?
I joined this university in 2020. And before it, I was in industry, in metal powder industry for about a little bit over 20 years, and earned experience in processes in powder metallurgy. And it was, in fact, a good match, good combination with metal FDM. So powder metallurgy technologies include also debinding and sintering.
Yes.
And then we in fuse deposition modeling, or FFF. We have this combination between, shall we say, extrusion,
yes,
and powder metallurgy or metal injection molding. And Professor BG, in fact, pointed out it with sustainability and affordability just of this fuse deposition modeling. And I think we are going forward in this route. We already published a paper on sintered samples with air sintering, and we have another paper in the pipeline. And I think BG, you can continue with this impact on society with the affordable and sustainable printing.
Yeah, that's a big need for it. We have a nice group of companies we're working together with here. So yeah, we see it's like a big future, but to make it a bit more affordable than it is today, I think that's a challenge, and that's really a fantastic market for it. But there are questions to answer before we really are there, I think.
Amogh, what drew you to additive manufacturing?
Yeah, I actually started off with my research in subtractive manufacturing, to be honest. So it was a few years back, not until the establishment of the Fab Lab in Halmstad University. That's when my focus turned into additive manufacturing. So I think it was in 2017, wasn't it, BG, when it was established. So during that time, I just started off like an hobby project, just to see how things go and just to learn the 3D printers that we had. And then soon that became very much research interest. And also there were some collaborations that we did with other universities where they worked with metal additive manufacturing. So that also, as I said before, my focus was mainly on surface quality analysis of these printed products. So we at Halmstad University, we are experts in polymer-based additive manufacturing, and soon we are moving towards metal-based additive manufacturing. And thanks to you and your company, so that we are moving towards that slowly and steadily.
Oh, super. So you mentioned, Senad, that you recently published a paper. Tell us about that. Tell us about your work with FDM or FFF, metal 3D printing.
Yeah, I'm gonna start with this tensile stress bar.
Yes.
I think now, so this is one sintered, and everyone knows, everyone who is in the area of mechanical engineering or mechanical design knows that mechanical properties of materials are very important to consider when designing some product. And if one would like to present some basic data for designers, for all people in this process, normally it is started with tensile stress and hardness measurement. So the paper we presented on Swedish Production Symposium in Skövde in April this year was just focused to do 3D printing, do debinding, do air sintering, following and little bit modifying suggestions from the virtual Foundry.
Yes.
And do the tensile testing, the hardness, investigate the surfaces of the broken parts, and in that way provide some very basic, essential information to people who are thinking about to designing some products in sintered bronze, for example.
Yes.
And I think we presented some realistic picture. We also included some references from continuous casted processes for bronze, and some references from other type of additive manufacturing. And in some way, these are first results. It is one of, shall I say, very first systematic studies in this subject.
Yes.
And we will be very happy to see more studies. So now we have some first information, and now we see forward that we and all colleagues of us around the world are going forward and improve this sustainable and affordable metal FDM. And what we like in particular, all three of us, is this type of open architecture.
Yes.
So that you buy material, you are free to choose your printer, you are free to choose your debinding and sintering furnace, and that we have a community so that every one of us is enabled in some way to get the best configuration of a manufacturing process, manufacturing route that fit requirements of a specific product. And I think this is such a great thing with this opportunity to contribute to this open architecture.
But yeah, thank you for that. We completely agree. BG, you're about to say something.
Oh, yes. Okay, maybe it's easier. Yeah.
Yes.
So we call the project is Sunprint here, and it's about making things affordable here. We all know that metal printing is here and performs beautifully, but not to a price which makes it accessible for small companies or private persons and so on. So using single printers, and you can also see here is just a picture of the companies we have been connecting to this project here through our Fab Lab, because they are partners in the Fab Lab here, industrial partners. And for instance, we have the military here who
Yes.
are the Swedish military armed forces are really interested also to make spare parts and so on in the field here. So as an example of applications here. So, but and we have done some nice things here. We are also not only doing tensile bars, we also have we are making more advanced structures like impellers for
yes.
outboard engines. And actually, I don't know what is this part here you have here.
It is a part for car industry, something for chassis.
Yeah. And we have a lot of different of your material types also available here for different to let our partners work with. This is just one part of the heap of the. We have done some work also in the aluminum materials. We have started to.
Yes, we have started.
I think aluminum was the first one that you tried. Is that right?
Yeah, I think that was first, and then we went back to the bronze. We went to the bronze materials for different reasons there. But,
Now, BG, you showed that list of companies at the bottom of that poster. What type of companies are those, and what sorts of parts are they looking for as you start working with them?
Well, we have one company called Maison, or named Maison, who are doing ventiles for the offshore and marine applications there. And for sure, they need to, their customers, they need to have quick access to spare parts or replacement. Ships are just staying very shortly in the harbor, and it can happen all over the world where they need a spare part and so on. So yes. This is a way for them to distribute their manufacturing. Let's see, what other companies did we have? We have something called Deacon Wheels, who are making also, they make a special unit to put in a roller chair, for disabled people there. So to connect this motor unit, they need some for each type of you call it roller chairs, or what do you call them?
Wheelchairs. Wheelchair. Yeah.
Wheelchair. Yeah. Wheelchairs. Yeah. Anyhow. That is each of them, they have a different sort of design, so you need to have a special tailor-made connection. So this is very useful for them to make products in that way. Yes, what else? And I guess I mentioned the militaries for looking for ways to in the field to make simple replacement products there. And we also have like a Tyler Halo. They're making, well, Sweden is very special. It's very cold here, as you know. It's like ice bears are roaming the streets and everything, and we have lots of snow here. So saunas are very popular here. So we have close to university in lab, we have a Tyler sauna, which is a quite well-known brand in the field there. And they also are talking about spare parts and so on in order to make that without doing the huge investment it takes to when you are using other laser techniques, for instance, SLS and so on.
So instead of stocking several of every part that you might ever need, you're just stocking spools of filament and you've got your equipment there and you're able to make many different kinds of parts with that one platform, so to say.
Yeah. We're just shipping your drawings to anywhere in the world, and that you can make for the ship. This Maison company, they can make the spare parts very easily for their customers everywhere, anywhere.
Now, the paper did just some research on the process itself, the results when you're following the process. You said that you made some adjustments to what we publish. Talk about those results a little bit. How do they compare to manufacturing processes that have been in place for a while?
Yeah, in classical powder metallurgy, we do have a very high volume or mass production.
Yes.
And this is the reason that all the processing times are as short as possible. And they are prepared for, shall I say, quite large investment in the start to be able to produce a lot of parts. Here, we are starting with quite small investments. And here we are also having opportunity to produce on demand in order to remove a large stock in some storage. And so we should be able to make a lot of changes for a very short time and fit to process from aluminum, bronze, steel, titanium to products made of very different materials. And just taking bronze, for example, we have sintering temperature of 870 centigrade.
Mm-hmm.
And it is not that high. Before it, we have this, shall I start? We start first with printing. Amogh, could you please start with some description of printing?
Okay. So I think we have come a far way now with printing process, because when we first started, there was some problems, both from our side, from the printing equipment side, and also from the material, because it's quite natural, because we have a very high metal powder content in these filaments, so it is quite easy to snap when we are printing. But I think it's safe to say now that the material development has been immense with virtual foundry, because we are not facing that issue anymore. But at the same time, we had some sintering problems. I think Senad here can describe those things much better than me. So because of these sintering problems that we faced, we had to come up with one small enclosure for the printing process itself, so that the printing takes place in a controlled environment, so that we get the better mechanical properties and so on. So, and you can see from this video also that we have made a small enclosure, built it. Actually, I built it myself, this small enclosure for this printing process. So with that one, I think we have some latest results, which Senad earlier showed, that we made these tensile bars, which was done in a controlled environment. So soon, next week, probably we'll be testing out the material properties. And then and that will be another paper that is soon to be published.
Great.
So, after printing, when it was finished, and Amogh had a lot of hours there to fix all small stuff that appeared, and then it was debinding, and I think recommendation from the beginning was 3 hours debinding and 480 centigrade. And then some preliminary tests we did showed that in our conditions, it was a little bit short time. So we prolonged it to 4 hours. And then after 4 hours, the sample was in a good condition. And it was of help. We did some literature review, and in one publication, we saw some typical appearance that match our appearance after 3 hours. So it was a strong signal, make it longer. So after 4 hours, the binding was good. Then we followed procedure to take it out the samples, put some activated carbon,
yes,
and put back an 870 centigrades, and for 3 hours. And then I think it was quite straightforward. And we let the samples cool down with the furnace.
Mm-hmm.
And we are very happy with the first outcome. And we got UTS approximately half of the reference, and hardness was about 1/3 of the reference.
Yes.
But to consider that the reference is full dense material, that continuous casting technology is shall I say, well-known technology with 100 years of experience, and here we have only few years in total that we are working with it. I mean, in the whole world.
yes,
So
less than 10.
yeah. So I said previously, now we have first results, and now we should take a look how to achieve even higher sinter density.
Yes.
How to proceed with printing, because the printing pattern could also help us in avoiding large accumulated cavities inside the samples.
Yes.
And now it's to take step by step. And our next step is, shall we say it now, Amogh?
Yes.
We did sintering in protected atmosphere, in active atmosphere, nitrogen, hydrogen, and we will see how it will look like in comparison to this common air sintering. And yeah, let us come in in a few weeks forward to the application.
Right.
And one small thing that I wanted to add was that printing in an enclosed container, like the one that we showed earlier, it does make a difference. So I think that is what we will be publishing as well in the coming paper.
Good.
So that makes a huge difference.
Right. How can people find out more about the work that you're doing, about Halmstad University, about the Fab Lab that you've built?
If you go into www.hh.se, you will come to the university, and there you can search for Fab Lab, or you directly just Google for Fab Lab Halmstad.
Okay.
you will have some info. I don't know the publications we just presented at the conference this spring here.
The publication is linked from the Virtual Foundry side.
Okay.
Website,
Yes,
so
that's perfect.
they
You
can
have
download it from the publisher,
Yeah,
and
yeah.
it's open source.
Yeah.
So
That's really nice. That's really
Okay.
nice.
So I will include links to all of those things in the video description so people can find it quickly and easily.
Mhm.
Is there anything else that you three would like to add to the discussion?
I would like to say something. Here we have such a large diversity of materials, processes, and so on. So it is just to encourage people to write down their investigation and to publish it, because there could be not one, but several processing routes which leads to successful products. So one route which may not be good for one producer could be very good for a third one. So let us encourage people to investigate and to publish and to share with all other people.
Terrific. Thank you for that, Senad, so much. People all over the world in universities like yours and other kinds of institutions are doing similar kinds of work and working with the materials, seeing what kind of results they get, and seeing what next steps can happen and where this technology can move into the future and help people make metal parts themselves and be more self-reliant. Thank you very much for the work that you've been doing. It's terrific. Now, I do have one more very important question for you before we wrap up today. What do you call somebody who says they are Swedish, but they really are not?
Hang-arounds.
You call them an artificial sweetener.
Sweden.
I'm so relieved that you laughed. They have to, trying to find some internationally humorous jokes can be a challenge sometimes. So I appreciate you humoring me and going along with that. Well, thank you all very much for joining me today. If you've got a really cool project you'd like to talk about in this format, reach out to info@thevirtualfoundry.com. If you've got a topic you'd like us to do a deep dive on in a podcast, reach out to info@thevirtualfoundry.com. We would love to do a podcast recording with or for you. In the meantime, like and subscribe, and happy painting, everybody.
Okay.
Perfect. Thank you.